Hi there, and welcome to our Chapter 16 lecture video. Today we're going to talk about oxidation and reduction, or what we shorthand as redox. Redox is a gain of electrons. Oxidation is a loss of electrons. Oxidation states are how we keep track of redox reactions. It's just a formalism. It's very similar to negative charge or atomic charge, but a little bit different. Half reactions is kind of like net reactions or ionic reactions, but it's more of a formalism for these redox reactions where we break down the reduction half, the oxidation half. If they add up, you should get the entire redox reaction. Now, it's commonly thought that oxidation is just the gaining of oxygen, and while that does work in a lot of cases, if we don't have oxygen, that, doesn't really work as a formalism. So it's better to think of oxidation as a loss of electrons and reduction as a gain of electrons. Now, oxygen is the second most oxidative element. It's kind of where we come up with the name. The only element more oxidative than oxygen is fluorine. And so the more pull for electrons, the more likely something is to oxidize things. Oxygen really wants to, steal electrons from things, so it oxidizes things while it gets reduced. And so this is what we call the oxidation reduction cycle. Depending on how you look at it, sometimes you can confuse yourself because the thing that does the oxidizing gets reduced. The thing that does the reducing gets oxidized. And so here we have a common reaction. H2 plus O2 goes to water. Now, in this reaction, hydrogen is being oxidized, making it the reducing agent. Like I said previously, the thing that is oxidized does the reducing. Whatever is doing the thing is called the agent. So whatever is doing the reducing is called the reducing agent. Likewise, whatever is doing the oxidize is the oxidizing agent. The oxidized agent is then reduced. Whenever we have pure elements that are turning into something other than pure elements, molecules that aren't diatomic or homodiatomic, that's a red flag that we have a redox reaction. They're going to change their oxidation state. In this case, we can think of hydrogen being neutral, oxygen being neutral because they're just bonded to themselves. There's no difference in electronegativity. Because of the difference of electronegativity between hydrogen and oxygen, we can think of oxygen as having more of the electrons. And so we would say that oxygen has a -2 oxidation state. Remember, oxygen always takes a -2 charge when it does ionic type stuff. And so when we give it an oxidation state, oxygen's always going to be -2. Hydrogen, we always mention, hydrogen is either always +1 or -1 in the ionic state. And so its oxidation state is always going to be +1 or -1. For neutral compounds, your oxidation states of everything should sum together to be 0. So we have an oxidation state of oxygen on -2. We have 2 hydrogens that have an oxidation state of +1. 2 +1s cancels out a -2. And so everything works out. And this is just a formalism. This isn't to say that these things actually have charge. It's just a way of, keeping track of electrons. And so here are 2 common mnemonics for remembering what oxidation and reduction is. I prefer oil rig, but some people like, Leo the Lion says GER. These are both saying the same thing, just rearranging the letters, so to speak. So we had already mentioned this. I had given the prelude to it, but oxidation state, oxidation number, these are just bookkeeping for electrons for redox reactions. You can apply an oxidation state to anything, but it's only really going to change in redox reactions, and so we only really ascribe it to elements and molecules, ions, when we're doing this type of chemistry. And so the book does point out that oxidation state shouldn't be confused with ionic charge, but it is very similar. And if you have a monatomic species, ionic charge and oxidation state are identical for single atomic species. So if you just have a single atom, a single ion, it's safe to say that the oxidation state is the ion charge. When you have polyatomics or molecules, that's when you have to be careful not to directly associate charge with oxidation state. So here are just 5 rules. We're going to go over these, but in general, they're very similar to a lot of our other rules. Elements are always neutral, and then everything else is kind of determined on electronegativity. Whether you ascribe it a positive or a negative is going to be determined on whether it's more or less electronegative, or what type of monatomic ion it forms. So if we consider everything as a monatomic ion, then ionic charge is equal to oxidation state. So we just have to make sure not to do this with polyatomics and break the polyatomics into their atomic species. These are just rules that we know from associating charge. Group 1 metals always have a +1 charge. Well, a group 1 metal will always have a +1 oxidation state because we're talking about just the individual metal. We're not talking about polyatomic. We're talking about just the monatomic ion. The monatomic ion charge will always be equal to the oxidation state. So, first off, we could ascribe all of the oxidation states, but the first thing we should see is that calcium is a pure element here, and hydrogen is a pure element here. That is your red flag for these two things are the redox pair. Now you have to figure out which one's being reduced, which one is losing electrons, which one's gaining electrons. And in this case, we can see that calcium is being oxidized because it gives up its electrons. So it goes from the 0, the neutral state as an element, to a +2 ionic species. Hydrogen goes from +1 to 0. The elemental species is always neutral, and going from +1 to 0 is a loss of charge or an increase of negative charge. It's a loss of positive charge, but an increase of negative charge. So in chemistry, when we add things, we're making things more negative. When we take things away, we make them more positive. It's kind of the opposite of our intuition, because when we're moving things, when we're adding or taking away things, the only thing we typically add or take away is electrons. Especially in oxidation reduction reactions, we're just following the electrons. And so here would be another example of a redox reaction. Now we don't have two pure elements. We do have tin. Tin is turning into tin oxide. So we can guess that tin is being oxidized just from the fact that it's gaining more oxygens. We could then go and look, okay, oxygen's always a 2-. That means that tin has to be a 4+. So yeah, tin's getting a 4 electron oxidation. But what's getting reduced? In order to do that, you actually have to assign the oxidation states. If we assign the oxidation state to this nitrogen, we'll see that it's a +5, whereas this nitrogen is a +4. And so tin is getting oxidized 4 times. It's losing 4 electrons. But nitrogen is getting reduced 4 times. It's gaining 4 electrons. And that's why 4 molecules of nitric acid will turn into 4 molecules of nitrogen dioxide and 2 molecules of water. Just like every other reaction, we have special rules of how we balance reactions. Redox reactions, we typically break into half reactions, looking at the redox half, looking at the oxidation half, and then combining them to make sure that they make sense just like the actual chemical reaction would. And so, in this case, we could just split up what's being oxidized and what is being reduced. We say what is being oxidized is the oxidation half reaction. What is being reduced is the reduction half reaction. However, we're not quite complete because aluminum can't just turn into aluminum 3+. It has to give off some amount of electrons in order to get that +3 charge. So we simply just say that aluminum turns into aluminum 3+ plus 3 electrons. Likewise, silver plus can't turn into silver 0 without first gaining an electron. However, we will also see that for this reaction to be balanced, we have to have the same number of electrons that are being donated as that are being received. And so we can just use stoichiometric coefficients to do the same thing that we did in chapter 7, 8, and all the other chapters that we've looked at reaction stoichiometry. And so whatever is in the products of one reaction and the starting materials of another reaction will cancel out. And we can say that aluminum metal reacts with 3 aqueous silver molecules to form aqueous aluminum and 3 solid silver molecules, or moles, equivalents, whatever, measurement metric we're using for the case. So we always want to make sure that everything is balanced. This is just our fundamental rules. Review the rules more fundamentally, but they're very similar to what we've been doing the whole time. Just now we're considering electrons instead of just the elements in molecules. So, everything equals out, just like we always make sure. If you want to do some type of, crosshatch or plot that makes sure that you keep track of everything, that's a wise decision until you get really comfortable with things. When I'm doing complicated reactions, I'll still, keep some type of note-keeping system. Here are just the summarized rules from, the previous slides. You can pause and take a picture, write them down, whatever is best, but these are also in your textbook. We can also look at specific rules for when we do redox reactions in acidic media or basic media. We follow all the same rules except for when we're balancing things. We leave hydrogen and oxygen for the very end. Oxygen gets balanced by adding extra water molecules. Hydrogen gets balanced on the corresponding side by adding more protons or H plus molecules. All the other rules are identical, and basic solutions will deal with OH minus because hydroxide is our quintessential base, H plus is our quintessential acid. Here's how it would look if we have this type of reaction. This is just an ionic reaction. We need to know what other chemicals are actually involved because I minus and chromate don't just exist in a vacuum. And chromium 3 plus doesn't just exist all by itself. These have counter species associated with them. And so we can first break into our redox half reactions. The oxidation would be the one that, loses electrons, goes from a negative charge to a more positive charge, in this case, a neutral charge. Chromium, we have to figure out, first, what is the charge of chromium? Because we're told what chromium 3 plus is. It's just 3 plus. But chromate, you might not memorize that chromate is a 6 plus version of chromium. If you do, it's nice forward. It's, just a 3 electron reduction. These would be the half reactions without any electrons. We then need to, balance the electrons. We can balance the electrons by adding protons and water for the acidic reaction. So the book kind of sets this up so that we do the balancing of the waters and the H pluses first and then the electrons. But honestly, the order doesn't matter. I typically balance the electrons first because that's how my brain works. And then I remember that I need to balance the H pluses and the H2Os because that's kind of just the secondary thing that comes in my head. If you want to balance the waters and H pluses first or the H pluses hydroxides first, if you're doing a basic reaction, totally fine. It's up to you. And so we can add both half reactions together and we should get the net redox reaction. Now it actually makes sense because chromate and iodine can be associated to these positive ions. There's waters and other things to solvate the chromium plus. We are in an aqueous solution. Where's the water coming from? Now we have some more stuff accounted for. Same exact rules for doing redox reactions in basic media. Except for now, whenever we add an H plus, there needs to be an OH minus to neutralize it out. This is how we're creating the water, so to speak. Just the rest of the rules that were the same as before. We're not really going to do too many redox reactions in acidic media versus basic media. That's more for, if you're really doing battery reactions, that's for a Gen Chem class. We're going to introduce these things. We're going to focus mainly on just the base redox reactions like we showed in the very first 2 examples. So we can look at reactivity series when we talk about redox reactions. The book just gives you one activity series, not reactivity series. You can look at both redox potentials and oxidation potentials. What the book presents and what I'm going to show right now is just redox potentials, but we have the ability to look at things in terms of redox reduction or oxidation. It just happens that the activation series of metals that's given is just for redox potentials. And so depending on, if you're more oxidative or more reductive, you're either going to favor the the reduction reaction or the oxidation reaction. If you're looking at a reduction potential map, like we're going to right now, the forward reaction would be the redox reaction. The reverse reaction would be the oxidation reaction. If we were looking at an oxidation potential, diagram, map, tablature, it would be the opposite. The forward reaction would be the oxidation reaction. The reverse reaction would be the reduction reaction. The energies are switched. So If I reduce something, I'm going to have a negative energy. I'm gaining some amount of electrons. If I'm doing an oxidation, I'm losing some amount of electrons. And so the energies need to reflect those type of events. So here, lithium is a very high reduction potential metal. So it really, really wants to give off electrons. Whereas gold really wants to hold on to its electrons. It has a high oxidative potential, but a very low reduction potential. Whereas lithium really wants to reduce things or de-oxidize. Gold really wants to oxidize things or be reduced. So we could look at a reduction or oxidation potential series and predict whether a reaction is going to happen. Since we have a reduction potential series, magnesium was higher on the reduction potential series than copper. So magnesium wants to reduce copper and be oxidized itself. So since magnesium is all the way up here and copper is all the way down here, we would say that the forward reaction for magnesium is going to be favorable, while the reverse reaction for copper is going to be favorable when they're paired together. In this case, magnesium would rather be magnesium 2 plus, and copper 2 plus would rather be copper metal. Both of them are happy with that arrangement, and so the reaction occurs. If we watch this experimentally, we can dip some magnesium into some copper solution, typically copper sulfate or copper nitrate. This is probably a copper sulfate solution since it's blue. And so we get copper metal and some magnesium sulfate, presumably aqueous solution. And so we could do the same thing with iron and magnesium. However, magnesium is higher on the reduction potential. So magnesium would rather reduce iron than let iron reduce it. Magnesium does not want to be oxidized from the 2 plus back to the 0 metal state. So this would not be a spontaneous reaction. We would actually have to add energy to this reaction to get it to go. And so this would not be a spontaneous reaction. We can look at, metal ions or metals being dissolved by acid in the previous lecture, acid-base lecture from chapter 14. The way that we can actually determine which acids will dissolve which metals is by the redox potential. If the redox potential is, lower than H2, then you'll have a successful reduction reaction. If, the redox potentials don't make sense, then you'd have to add energy or add some electrical current to get that metal to dissolve via some acid. So we could look at zinc and see if it dissolves. If we check the redox potentials, zinc does have an appropriate redox potential so that it can reduce H plus back to hydrogen gas. This is a favorable reaction. It's very fun. You can just drop some zinc metal and some hydrochloric acid. And if you have a ignition source above the flask that you're working with, you'll just hear the pops that come from igniting hydrogen gas and turning it back into water. And so the last thing we're going to really talk about and focus on is batteries. Batteries are probably the most useful and common, redox device you use. Combustion engines are also a very common redox device, except for instead of harvesting the electricity, we're just harvesting the energy put out by the reaction. So slightly different outputs that we're concerned with, but the same fundamental type of reaction. And so we have a whole bunch of different types of batteries. The most simple type of battery is the voltaic or galvanic cells. And these are composed of two different cells that have, either negative or positive charges associated with them. We break this into an anode and a cathode. Most batteries have an anode and cathode. These are just the earliest advents of the battery. And so typically the anode is associated with the negative sign because negative ions are going to travel towards the anode. The anode is doing the oxidation reaction. And so when the metal turns positive, those negative ions are going to flow towards the anode to make sure that everything is still neutral. Even though we're changing charge, we're transferring electrons, all of the molecular species need to be charge balanced. And so zinc metal will get oxidized at the anode, nitrate will come over to zinc ions, and then you'll have zinc nitrate solution. Whereas the copper nitrate solution is being reduced back into copper metal. This is basically just saying what we've already said. If you have a dead battery, this is when the reaction has completely completed. It's completely done. There's no more electrons that can transfer. And so in order to recharge that battery, we have to apply the same electric potential that was given off by the battery to regenerate the battery. Not all batteries are regenerative. Typically, this is more an engineering issue than a chemistry issue. And so when your batteries on your phone stop working, it's not because the lithium ions disappear or they're no longer reactive. It's actually because of physical dendrites that form that block the recharging or the regeneration of parts of the battery. And ultimately, that gives you a shorter battery life until the battery is no longer useful. But if we can regenerate the battery, you just fully place all of the ions back into the metal state so that they can then be reused for whatever energy device you have. Dry cell batteries are a much more useful battery. Dry cells are more dense, so liquids are less dense than solids. So if you can make your electrolyte a solid instead of a liquid, you've just made the energy density of your battery greater. And that's, always what we're looking for. Bigger bang for your buck. And so dry cell batteries are the way that we do that. Your cell phones are all dry cell batteries where you have, a cathode, an anode. Instead of having some moist paste, you actually have intercalation between the anode and cathode where you have lithium dissolved into a graphite material. It's very complicated and doesn't work as well as some of the older batteries like this one would. However, these, zinc manganate batteries are not very they're not very energetic like the lithium ion batteries that we have in cars or cell phones, computers, things like that. So, just kind of saying the same thing. Lead acid batteries are another very common battery that you deal with every day if you have a car. And so these are your car batteries. You have lead at the anode. Typically, your anode is some pure metal. Your cathode is usually some carbon or metal salt or metal ion. H2SO4 or sulfuric acid happens to be the electrolyte because it can generate sulfate ions in solution. So those sulfate ions are what's going to transfer the electrons from the anode to the cathode and ultimately power your device. And so this is the reaction. We can break that up into the half reactions if we want to. Oxidation, reduction. We need to make sure the amount of electrons given off are the same as the amount of electrons that are accepted. We can then come up with our, balanced redox reaction. But, there are problems with regenerating these batteries. And so if you, do certain things for certain systems, in the case of, a lead acid battery, if you run it for too long without charging it, so if the potential drops to such a low level, you can never regenerate it. Likewise, with lithium-ion batteries, if you cycle them too many times, millions of times, eventually you grow formations that block the recharging. And so this happens with all batteries. We're constantly just working to engineer better setups so that the physical situation doesn't impede the chemistry. We also have hydrogen fuel cells. So the book talks a lot about fuel cells. Hydrogen fuel cells are the most common fuel cell that you'll see. It's the really only commercially viable fuel cell that exists now. There are ammonia and nitrogen fuel cells, but they're just not energetically as efficient as, the hydrogen, oxygen, or water fuel cells. And so the idea is that you can do electrolysis or pass an electrical current through water. This turns it into H2 and O2, which can then be harvested and combusted later for energy. The same amount of energy that you have to electrolyze water with is the energy you get out of the combustion reaction afterwards. And so that's how we have fuel cell batteries. Electrolysis has a whole bunch of applications, from actual reaction chemistry to just regenerating different materials, electroplating. But in the case of the hydrogen cell, we have some amount of water that is hooked up to a current. That current then separates the oxygen and oxygen and hydrogen from water. If you have a way to contain or store those gases, you can, use them at a later time to generate energy for combustion or whatever else you want to do. Like I had just mentioned, we can use electrolysis to refine things. And so that's often how we refine a number of metals that aren't stable in the pure elemental states. We can also use this for electroplating. So if you have some expensive or pretty metal, you can take something very cheap or ugly and coat the nicer, veneer around the core, so to speak. And so we do this often with chrome plating, gold plating, silver plating. This would be the reaction. We'd have some amount of silver ions dissolve, like silver nitrate. You could then insert some material that you wanted to be plated, apply the electric current. The silver ions will go onto the new object because you are applying the energy required to do the unfavorable reaction. Talked about a whole bunch of things between oxidation reduction. We covered oxidation states. We covered, reduction potentials, oxidation potentials, how you can use them to predict spontaneous reactions. Batteries were kind of the last thing we talked about, including fuel cells. We're not going to, do too many questions on batteries, but you should have an idea about them. You use one every single day, no matter, where you live in the US, you interact with batteries. And so the main focus is going to be defining redox. Reduction is a loss of electrons. Oxidation is a loss of electrons. Reduction is a gain of electrons. You can use your mnemonics to remember that, or you can just remember things on the left side of the periodic table tend to be reducing agents. Things on the right side of the periodic table tend to be oxidizing agents. Things over and near oxygen tend to oxidize things. Things that are far away from oxygen, like the alkali metals like lithium, tend to reduce things. Half reactions are just how we communicate redox reactions. We break them into the redox half and the oxidation half. If you have any questions for me, make sure you reach out during office hours. Otherwise, I'll see you in lab this upcoming